Alright, we're talking about inscribed angles today. An inscribed angle is an angle with its vertex on the circle and whose sides contain chords of the circle. So down here in this picture, it says name all of the inscribed angles and their corresponding intercepted arcs below. We have 3 inscribed angles. One of those inscribed angles is angle ODG. Angle ODG. Notice that the vertex D is on the circle, and both sides of that angle are chords of the circle. Line segment DO and line segment DG are chords of that circle. And its intercepted arc is arc OG. So that's one inscribed angle and its intercepted arc. Another inscribed angle would be this angle. Angle DOG. O is its vertex, it's on the circle. Angle DOG. And its sides are chords. Line segment OD and line segment OG are chords. And its intercepted arc would be this arc right here, arc DG. Angle DOG and its intercepted arc DG. Okay, so that's 2 of them. The other inscribed angle we have is this one right here. Angle DGO. This angle right here. Angle DGO. Again, the vertex is on the circle. The sides of the angle are chords, line segment DG and line segment OG. And its intercepted arc would be arc DO. So those are some examples of inscribed angles and intercepted arcs. Let's read this theorem right below. It says, if an angle is inscribed in a circle, then the measure of the angle is half the measure of the intercepted arc. So I don't know the measurements of all this stuff, but let's just say that arc OG is 120 degrees. That would tell me, based on this theorem, that angle ODG has to be 60 degrees, because it told me that an inscribed angle is always half of its intercepted arc, and half of 120 is 60. So let's see if we can take that theorem and solve the problem below. Given that the measure of arc BC here, is 100 degrees, find the value of x in circle O. Alright, now x is labeling this angle. Its intercept, that's an inscribed angle. Notice the vertex is on the circle. You got a couple of chords for sides. Its intercepted arc is arc AB. So if we figure out what arc AB is, this angle will be half of that. Well, line segment AC is a diameter. And remember, a diameter splits the circle into a couple of semicircles. And each semicircle is 180 degrees. So this semicircle has been split into 2 parts, but those parts got to add up to 180. So if this part's 100, then I know that the other part has to be 80 degrees. So if this arc's 80, remember the inscribed angle is always half of that, and half of 80 is 40. So I know that x is 40. Alright, let's try this next theorem. The next theorem says if 2 inscribed angles of a circle or congruent circles intercept congruent arcs or the same arc, then the angles are congruent. Okay, well, if the inscribed angle is always half the intercepted arc, if you got 2 different inscribed angles with the same length arc, they're both going to be half of the same number. They're going to end up being the same. So it should be pretty kind of common sense, self-explanatory if you understood the previous theorem. But let's go ahead and take that theorem and do example 3. In circle Q, the measure of arc ST is 68 degrees from S to T. Find the measure of angle 1 and the measure of angle 2. Alright, well, angle 1 here, if I follow the sides of that angle, its intercepted arc is this 68 degrees. If I follow angle 2 and its sides, its intercepted arc is also this 68 degree angle. So based on that theorem we just finished reading, they both have the same intercepted arc, then those angles are going to have to be congruent. And it would make sense if I just focused on angle 1 for right now. The inscribed angle is half of the intercepted arc. Well, what's half of 68? It's 34. And then if I went and found angle 2, that inscribed angle has an intercepted arc of 68. What's half of 68? 34 again. And they would just happen to come out to be the same. Now, because of that theorem we just learned, once I find one of the angles, I can already know what the other one is without having to really give it any more thought. I know they're going to come out congruent. They're both going to be 34 in this case. All right, the next theorem says if an inscribed angle of a circle intercepts a semicircle, then the angle is a right angle. Well, again, this should be some common sense based off of what we already learned. A semicircle is 180 degrees. And we said an inscribed angle is half of its intercepted arc. So if it's intercepting a 180 degree arc, it should be half of that. And half of 180 is 90. And that's exactly what a right angle is. It's 90 degrees. So this, again, really just follows the same theorem that we learned the first time. Right here in this example, notice this inscribed angle, angle FEG, and notice its intercepted arc. Because line segment FG is a diameter, I know that arc FG is a semicircle. I know it's 180 degrees. So anytime you have an inscribed angle with an intercepted arc that's a semicircle, 180 degrees, it's going to be half of that. It's going to be a right angle. It's going to be 90 degrees. All right, let's see if we can take everything we've been learning and solve all this stuff that we have going on example 5. All right, so in circle A, the measure of angle 1 is 6x plus 11. The measure of angle 2 is 9x plus 19. Now, those are not intercepting the same arc. Angle 2 is intercepting this arc. And angle 1 is intercepting this arc. Now, what I do notice about those two arcs is that together those two arcs form a semicircle. So I know these arcs add up to 180. Well, these inscribed angles are half of those arcs. So if the arcs are adding up to 180, then the angles got to add up to half of that. They got to add up to 90. So I'm going to take those two expressions and I'm going to add them together and set it equal to 90. So when I do that, the first thing I do is combine like terms. 6x and 9x is 15x's. And we got 11 and 19 is 30. So I subtract the 30. And divide off the 15. And that tells me x is 4. Now my goal is not to find that x is 4. I want to find out what angle 1 and angle 2 are. So I have expressions for each one. Now that I know what x is, I can just substitute that back in. So for angle 1 is 6x plus 11. Get a little confusing with all this stuff here. Since x is 4, I can just substitute that 4 in there for x. 6 times 4 is 24. 24 plus 11 is 35. So I know angle 1 is 35 degrees. Now, I set up this equation based on the fact that I know these two angles add up to 90. So if I know this angle is 35, I can just subtract that from 90 and get the answer. Now, the drawback to doing it that way is that if I messed up somewhere in here, I won't realize that I've messed up and I'll get both my answers wrong. So one way to check my work and make sure that I've done the right thing is to go ahead and solve for angle 2 just like I did angle 1 and substitute into that expression. Angle 2 is 9x plus 19. So if I substitute 4 in for x, I got 9 times 4 is 36. 36 plus 19 is 55. And then I can check myself. Do they add up to 90? Yes, they do, so I can feel confident that what I've done is correct and I didn't make any mistakes. All right, so we got angle 1 and angle 2. Angle 3 is 4y minus 25, and angle 4 is 3y minus 9. And it tells me right here that arc PQ is congruent to arc RS. Remember that theorem we had, if you got two angles, two inscribed angles, and they have congruent intercepted arcs, then those angles are going to be congruent. Because whatever this number is, angle 3 is half of that. And if this is the exact same thing, when you do half of that, you're going to get the same thing you got for angle 3. These are congruent angles. So what I need to do next is I need to take those two angles and set them equal to each other because I know they're congruent. I know they have equal measures. So I'm doing 4y minus 25 equals 3y minus 9. I'm trying to squeeze all this work into a small space here. All right. Can't have that y on both sides. I'm going to subtract 3y to get rid of it on one side. And then I'm going to add 25. And a negative 9 plus 25 is a positive 16. So no, y is 16. Now again, just like earlier, my goal was not just to solve for the variable. The variable is going to help me solve for the measures of angle 3 and 4. So I need to substitute that back in. So angle 3 is 4y minus 25. So since I know y is 16, I'm plugging 16 in there. And we're doing 4 times 16 minus 25. And that should give us 39. Now, I set up this equation earlier knowing that angle 3 and 4 were congruent. So if I know angle 3 is 39, angle 4 should be 39 also. Again, if I'm in a hurry, I can go ahead and throw that on there. But if I want to just check and make sure I didn't make any mistakes, I'm going to take the expression for angle 4 and I'm going to substitute in there as well and just make sure I get the correct answer. So I'm putting 16 in for y. So I got 3 times 16 plus 9, minus 9. And I do get 39. So I got two angles that are congruent there like I was supposed to, so I can feel confident that I did everything correctly when I was solving for those angles. All right, we got another theorem. This theorem says if a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. When we inscribe a quadrilateral inside a circle, each vertex of that quadrilateral should be on the circle. And it says its opposite angles are supplementary. So here on example 6, it says quadrilateral QRST is inscribed in circle C. Notice each vertex is on the circle. If angle T is equal to 95 degrees and angle S is 100 degrees, find the measure of angle Q and the measure of angle R. Well, we just read a theorem that said the opposite angles are supplementary. So that means that T and R are going to be supplementary. And remember, supplementary means they have a sum of 180. They add up to 180. Well, if I know they add up to 180, and I know one of them is 95, I can just subtract 95 from 180, and that'll give me the other angle. So I know that angle R has to be 85 degrees. And then angle S and angle Q are opposite angles. They got to be supplementary. So if I do 180 minus 100, that tells me what angle Q is. And so I know angle Q is 80 degrees. All right, let's look at example 7. It says find the value of the inscribed angle. All right. This inscribed angle has an intercepted arc of xy. Now remember that this inscribed angle is half of the intercepted arc. Now they didn't give us the intercepted arc, but they did give me this angle, and this is a central angle. And remember, we learned earlier in this unit that a central angle is the same as the intercepted arc. So if this symbol means right angle or 90 degrees, so that means this arc is 90 degrees. And therefore, I know the inscribed angle is half of that. So half of 90 is 45. So I know that angle is 45 degrees. The measure of angle XZY, 45 degrees. Alright, example 8. Find the value of x. Alright, they gave me an expression for this angle, this inscribed angle. I know this inscribed angle is equal to half of its intercepted arc. So I need to set up an equation to solve for x. The inscribed angle is equal to half of its intercepted arc. Well, what's half of 120? It's 60. So I can set that equal to 60, and then we're just solving an equation. I want to get x by itself, so I'm going to get rid of this 3. It was being subtracted, so I need to do the opposite operation, and I add 3. And then x is being multiplied by 3, so if I want to get rid of that 3, I do the opposite operation, divide by 3. And that tells me x needs to be 21. That's the only number x can be where that inscribed angle will be half of its intercepted arc like it has to be. Alright, we got one more problem. That's example 9. Hexagon ABCDEF is inscribed in circle O. All sides of ABCDEF are congruent. Find the following. Alright, if all these sides are congruent, that means we have an equilateral hexagon. And when it's inscribed in that circle, if it's going to be equilateral, it's going to have to be equiangular as well. This is a regular polygon, a regular hexagon. Okay. This circle is being split up into arcs, and it's being split up into 6 congruent arcs. Well, there's 360 degrees in a circle, so if you take that 360 degrees and split it up into 6 congruent parts, each one of those parts is going to be 60 degrees. So each one of these arcs is a 60-degree arc. Alright, let's find what we can find. We want to find the measure of arc CD. Alright, well, we just found that. The measure of arc CD, 60 degrees. Each one of those little arcs is 60 degrees. Alright, we want the measure of angle BFE. Angle BFE. Alright, there's angle BFE right there. Angle BFE has this intercepted arc. Alright, well, for this arc, there's 60 plus 60 plus 60. 3 times 60 is 180. And you might notice that if I were to draw this across here, this is a diameter, and I would know this is a semicircle. And remember, that semicircle, the arc is always going to be 180 degrees for a semicircle. So that inscribed angle, always half of the intercepted arc. Half of 180 is 90. So I know the measure of angle BFE is 90 degrees. And one more question, we want the measure of angle BCD. Angle BCD. There's angle BCD. It is also an inscribed angle. Notice the intercepted arc here. 60 plus 60 plus 60 plus 60. 4 times 60. That arc is 240 degrees. Well, the inscribed angle is always half of that intercepted arc. So half of 240 is 120. So I know the measure of angle BCD is 120 degrees.